So good morning. Yeah, so I will speak. I'll present some details about our research and some features that we implemented for the deep learning tooling. I think at this moment in time, a lot of people already know more about deep learning. What does it mean? And it's so common, so famous that I think I don't. So I decided to skip the introduction about the technical details. What is a neural network? All these things. I will jump directly to the results and the features and the implementation. So because I assume that the basic concepts are already familiar to you. But if you have questions, even if are basic questions or anything, just ask me. Don't. I can repeat. I can explain some details. It's fine. So what I'm going to cover today is some results related to what we added as features in Inspector for the deep learning module, basically the model assessment part, and also some results related to the research we are doing, and so which includes how to analyze generalization of models, how to improve generalization, and the proposal of today is to use ensembles. And some pictures about what we have as feature and ongoing research at Riscure. So what I'll try to cover today is some basic questions like if I have my neural network. So neural network is a machine learning system. I can put like that, where you put some label data into it. You train this network, and then you get some new data where the network never saw before, and the network tries to classify this data. So in this case, what we have here is supervised learning. So, and then when you do that for sidechain analysis, what you are trying to do is to classify leakages according to leakage models. So in the AES architecture, for instance, what you define as a leakage model can be the Hamming weight of intermediate state byte, and then you make your what you want to train your network to classify Hamming weights of intermediate bytes, for instance. And so, and when you do that, what you want to understand is in terms of model assessment is what exactly my network is learning from the data. I want to understand if the neural network is trained to learn actual leakage from data and not some noise or something random, because it's very common nowadays in the community that a neural network has the capacity of learning any data. So it can fit any random, even when you don't label correctly the data, it can fit those data. It can overfit it. So in sidechain analysis is also very common, and then it's important to have some metrics, some indications of what exactly the neural network is learning. If it's detecting the actual leakage, is discarding the noise, and so yeah. So and also the second part of the presentation, I will try to give you some indications through some practical results on how to interpret the generalization of the network, how to know if if you achieve a state and when you train your network that it's able to generalize to unseen data, and how do you make a good, let's say, conclusion about the validation of your model. And also I will give you some results about how to improve this generalization. So to summarize what have been done in the last 3-4 years, more or less, in the research progress that has been done for deep learning for sidechain analysis, I could let's say, separate in 5 groups. And I'm considering here the research papers that are published in conferences and journals. And we can see that let's say a big group of papers tries to implement deep learning as a profiled sidechain analysis, like template attacks, to bypass countermeasures, like masking, let's say, misalignment that is inserted as a countermeasure, and also combined with some methods like data augmentation to improve the capacity of the attack. So the second group so it deserves a group because it's a very distinct work, but it's the only one paper, I think it was presented in CHESS of this year, that the author used the neural network as the distinguish for sidechain analysis. So he trained a neural network for every key byte candidate, and then the neural network presenting the highest accuracy for the training, the metrics for the training presenting the best performance is considered as let's say as the best. Let's say the key is associated to that network. So the network itself is used as the distinguisher. So this is interesting work because it's a non-profiled attack. So you don't need to have label data. You don't need to do the profiling phase. So that's the interesting part of this work. The third group of research, it's mostly related to model interpretability, how to analyze what the network is learning, basically the learnability of neural networks. And the other group is the relationship between the deep learning metrics and side channel metrics. How to, let's say, how they are related to each other. Let's say guessing entropy, success rate, key ranking, how these metrics for side channel analysis are linked to metrics for deep learning, like accuracy, recall, precision, loss function, and this and so on. And so there is also one work that is I don't know exactly where it was published, but it's deep learning for leakage assessment, how to replace leakage assessment like TVLA or other metric t-test by deep learning itself, by the metrics of deep learning to validate the leakage detection. So we are adding one more group here. That is because it's a work that the report of this work is already available, but it's on ePrint, but it's not published in any conference. But we couldn't find a group to fit this idea. But then we created another group that is analyzing generalization, how to correctly analyze if the neural network can generalize to unseen data. And you can see that this field is becoming bigger and bigger because I could count more or less 70 research papers already on this topic in 3 years. So, and every year is more and more. So first year was something like 1 or 2, after was something like 10, and then 20 in this last year it was more than 40 papers. So I think this field is growing much more. I expect much better results and improvements in the coming years. So yeah, so just to keep it simple, I took this very common piñata traces with its AES, software AES, and protected very leaky target. And this is, yeah, so this is the correlation of the first key byte of the AES output, S-box output. And you can see that the correlation is quite high, so I think it is very easy to break this target. It's more or less Deer's region here. And so what I want to show you is these features that we have implemented here, that is salient features and input activation gradients. I'm in front of the screen, so it's not making anything easy here. So I would just run the module. So I'm going to attack the first AES key byte, this S-box output Hamming weight. It will take a few seconds, but it's the easiest way to share with you the results I want to present. I can take. Okay, so after the network is trained and validated, it will process something extra. That is, it's computing exactly where in the traces the network learns best, let's say, the features from the where the network is detecting leakage. So, okay, I got the key ranking. It's something that we had before, but now we have something more that is we have more output information. And the top one here shows what we call salient features, and it informs where exactly this neural network is detecting leakage from the implementation. So you can see the spikes here determines that those samples are the most important for each trace. So, and then the y-axis here, you see the frequency in which every sample was detected, the amount of time. So with this assessment, you can understand what more or less your network is learning from the traces, and then you can understand where the leakage is being detected. So it's a good information to understand if the network is learning leakage or purely noise. And there is another result that is input gradients. For each epoch, you can see every time the network processes all the training data, you can see what are the most important, the most sensitive samples for the network to make these decisions. So you can see that they stay high in the places where we see the correlation before. So Okay, so these are the features, but I will come back to the presentation to give you some details about that, how this is implemented. Okay, so the basic problem that we have is like this. So we have a neural network. This is a multiple layer perceptron, and we will provide input side channel traces, and then you get output that are probabilities that every class is associated to every label in the input in the training data. So what you want to know here is basically where in the input data the network is learning something to make such a decision, and how this is related to the hyperparameter, to the structure of the network. So this is a very common, let's say, research field for neural networks, image classifications. I think the right name for that is segmentation, because they take images of, let's say, a person or any or some object, and then they want to delimit where exactly every sample is associated to the object or to the person or to a car or whatever in this image. So for side channel application, we saw that could be useful to understand where the network is detecting leakage. So as you can see, so this assessment, yeah, I think I already said that you can basically map where in the input traces do you have points of interest, basically. So there is one paper that saw this opportunity to make points of interest selection for template attacks. So use this method for that. And also you can see how correct the model is, because if you see that the network is learning actual leakage or some specific parts of the leakage, then you can understand. You can see that you can assume the network is it's correctly set, and this is good for security assessment. This is interesting because if you know that your network is doing the correct job, then you don't overestimate the security of the target. Because if you set a completely wrong neural network, you don't break anything, you don't get anything, you assume that the target is secure, but maybe your network is not correct. So there are some existing methods to do this, and then the first one of the papers, research papers, decided to use occlusion techniques, and also another technique called layer-wise relevance propagation, which is a method similar to the one that we implemented. And this, I think, the most used one is the input activation gradients, because all these frameworks like TensorFlow, Keras, they all have building functions for that, so you don't need to implement this. This is already there, and this is, let's say, scientifically, it makes a lot of sense to use this method. But we also proposed something else, that is this backward activation path that I will show in one slide, a picture of how it works. And then we say that what this method detects are salient features. So the two results that I showed before, one is salient features, and the other is activation gradients. So input activation gradients is very simple to understand. So I decided just to put one equation here, but it's not complicated. So if you have the loss function, the function that computes the error of the network, there can be many types of different loss functions. And then what you do is you do a partial derivative of this loss function with respect to the one input sample. So I here could be is the index of every sample in the input trace. So this means the result of this derivative is the input gradient. So the explanation for that is of this equation it's here. So it means that a very little change in the inputs. It means that a very tiny or little change in the input sample makes a big impact in the loss function. So if you have this effect, it means that this sample is important for the network decision. So this is what basically this means. So the method that we implemented additionally is something that is not. So input activation gradients analyze the input information in the network. What we implemented is something that starts at the output of the network and goes into the input. So we analyze how, layer by layer, how the activation for the next neuron is affected by the previous ones. And so we do this backward path until we find the first layer, and then we map the 1 euro in the output to 1 euro in the input. So when we do that, we identify that this is the main decision path in the network. Okay, so this is just some technical details about the methods and some results. So just to validate, we did some simulated traces. I created a trace, simulated traces of 100 samples, and I defined that sample 68 contains exactly, let's say, the Hamming weight of my output, the S box of the output. And the rest of the samples are just random values. And then we can see that when I train the network with these simulated samples, it points to the sample where the leakage is located, let's say the label is located. So you already see the results in the real traces, so I will not focus too much on simulated ones. But I also did some tests on some masked implementation. I used this open source database. Okay, thank you. Which is the name of this database is ASCAD, and for fair comparisons, I decided to use this database because then you can reproduce the results with you and compare to these ones. So this ASCAD database, so there is protected and unprotected implementation. So you can see these are some results on the unprotected part and the unprotected AES, 1 kibyte only. This is the correlation of the S box output first kibyte, and this is the salient feature. So you can see that the network trained on a trace set where the leakage is located on this range, and the network make decisions exactly on the range where you see correlation. So it was just a validation on a leaky target. But we also were wondering how the network detects second order leakage. So then what we did next was to take the masked implementation, and first we validated the method on simulated traces. We used the same implementation they did for this AES on software, but we did some simulated traces just to verify. And then we put some, let's say this is a masked AES, where the mask values and the output in the S box masked output are placed on the sample 33 and 68. And if you correlate now, if you attack considering, let's say, an unprotected device, you don't get any leakage. If you do CPA, you don't get any leakage. So, but somehow the neural network labeled with as it would be an unprotected AES identifies where it can make decisions based on the mask values of the implementation. So meaning that it learns the mask and the output mask and combines them together to make the decision. And it's impressive that it just selects the samples where the masked values are located. So it somehow does a second order analysis here. It's a bit ambitious to say this is a second order analysis, but I could not see a more close explanation to something else, because it's just combining the two leakage into one, and then for me it's a second order result. And these are results on real traces. So you can see here, if this is the interval of the AES, I think kibyte 3, and this is this is when the trace is processing the mask value. So you can see if you correlate to the mask value that is available, you see it has a huge correlation. And this is the output of the masked S box. So you can see everything is masked, but when you train the network on these traces without knowledge of the masks, it learns exactly the samples where the mask and the S box masked is located. So it's again doing some sort of second order analysis, and then we can, with this the neural network training on that can break the target, and then we understand why, because it's just combine the mask values with the S box masked value. So I would say, yeah. So these are important metrics, I would say, for to understand where the network is learning in the traces, and also to see if it's learning from. So if you are an implementer, okay, let's say my mask is processed at this point. I want to understand if a network would be able to learn this mask. So then you can understand if this is happening, then you can see that your target's not protected enough. And then because a neural network is able to disclose that these mask values can be combined with something else. And then I believe this is an important assessment for this development phase. And yeah, so, and also when you do a first order analysis on your target, everything fails, it's worth to do this analysis because maybe some other method can detect second order leakage. Okay, so what I will present now, it's not so long, but it's just some results based on some last research we have done. That is to analyze the generalization of the network. So, because when you train a network, you want that to classify data that it never saw before. So how do you analyze this capability? That's basically the question. So the context is again supervised attacks, supervised learning, profiled sidechain analysis. And the questions here is which metric should I use to validate my neural network? Accuracy, precision, loss, what should I consider as the metric, and what is the most promising metric for that? And also how to improve the generalization. I will show you that using a technique called ensemble learning, it's a machine learning technique, it improves quite a lot the generalization of the network. So this picture summarizes the problem. Let's say on a leaky AES target, you train your network and then you analyze the training and test accuracies. And what you can see that the training accuracy usually goes high until it overfits the network. And the validation or test accuracy, it's high enough to break the target. Let's say if you get 55% of test accuracy, you can for sure recover the key. When you go to a Masked AES implementation, you see, okay, the training accuracy is also growing because the network has the capability to fit everything. However, the test accuracy stays very low, or under or around a random guessing, let's say. And then if you look to this metrics, you conclude, okay, the attack here is failing because the metrics are very poor. But in both cases, we got the key. So then we want to understand why exactly. So these metrics are not representing the side channel performance. That's the main conclusion here. And then we started to investigate how we can make this link between let's say the inconsistencies of metrics and sidechain analysis. So first thing is how to validate your model, how to decide when a model is correctly trained to go to the test phase. So this is the basic flow. You have training traces, you train your network, and then you get all the metrics from deep learning, your deep learning framework. And then you use the validation traces on the same neural network, and then you also get metrics. And the distance between the training and validation metrics is usually called generalization gap. And what you want to achieve is the minimum possible generalization gap, the minimum difference between accuracy, let's say validation and training accuracy, for instance. But we verify that these metrics here, deep learning metrics specifically, are not consistent, or not consistent enough for sidechain analysis. There is a paper on CHESS of this year that explains in some details about that, but we extended the work that they did to see which is the good metric, because they don't answer correctly the questions of maybe they don't, there's not that they don't answer, but they don't provide, let's say, a strong conclusion saying this is the best metric, this is not good, or this is the worst metric. But then we were a bit more ambitious here, and then we decided to say, okay, use this metric and not this one. So what we did here was to analyze, so we take this neural network and then we validate the network based on each different metric here, and we see how the success rate on different test traces would perform. And then if you use as a reference metric the accuracy, the recall, the loss, you see that the success rate never goes 100% this is a Masked AES implementation. And then if you consider the key ranking and validation traces is when you get the best success rate. So again, so we could see let's say the correctness of the conclusions from that paper, that the deep learning metrics are inconsistent for sidechain analysis. And then we saw that, not surprisingly, the key ranking for the validation traces is the best metric to validate a neural network. So you can see through this success rate chart that it's relatively better than the rest. So that's our conclusions on how to validate a model. But not only to validate, but also how to improve the generalization, how to make it generalize better to different traces. And then I could summarize 4 main methods for generalization improvement. One is data generation. Basically, instead of start some other techniques, you just collect more traces, and then which makes your network less capable to overfit the training data. But there's also other techniques like data augmentation, where you artificially modify the training data you already have, and also some regularization through other hyperparameters, which is more complicated because you increase the search space, but it's still efficient, but it's not, let's say, the most easy way to do that. And we also decided to test another method that is ensemble learning, which is a method to combine multiple, let's say you train multiple networks and combine the predictions of all of them into one, and then to see how it improves. So just to give a picture of how these ensembles are implemented for machine learning. So basically you have a big training set. Let's say you have hundreds of thousands of traces here, and you split the training set into small pieces, small training sets. Let's say 10,000 traces, 20,000, and this makes the training of each neural network easier because it's small. And then what you do then is to take the test predictions for all the different neural networks. For sure, you use the same test set on all the networks, and then you combine the predictions of them into one final prediction, in an ensemble. And then this, so the theory says that this always improves it slightly increases the results for the generalization, and also relax a little bit the need for fine-tuning hyperparameters, because if you have, let's say, 100 of networks here and a lot of them are wrong, the fluctuations of the wrong hyperparameters will be corrected by will be let's say compensated by the others. So at the first moment I thought, okay, but if I have, it will be like an average in the end and might not be good, but the results are quite impressive in the sense that it's not, so let's say the best, the result of the ensemble is usually as good as the best possible module that you train. And then this is, for us it improves quite a lot the generalization, but because in sidechain analysis, if you get 1% better classification accuracy, it's already something to break the key. And so every percent you get more, it's important. So this is the success rate of some test campaigns that we make. And you can see that the success rate by training, by combining all the ensembles, let's say all the neural networks, it's the best one always. And even if you get, let's say, the 3 best models out of all the networks you train, you're still not as good as combining all of them. And also, if you have condition to select the best model in all the campaign, which in our case we selected based on the key ranking because it was the best metric, it is still not good as combining all the predictions. So for us, ensembles works quite fine because it's always provided the best result in the compared to training all the separate networks. And so it's also important to say that this is a Masked AES implementation from that ASCAD database. And if you train this amount of, the available amount of traces is 200K traces. And if you train this, if you separately take 25,000 traces or 50,000 traces, not always that you recover the key for any module you put there. So any network you define. So But here you achieve 100% of success rate by training on small pieces of this training set. And also, this is the key ranking for all the models, all single models that we tried. You can see that they provide all different types of results. It's not always converging to the key byte rank is not always converging, but the ensembles are usually converging. So combining everything usually is the best that selecting, let's say, that training many times and try to just take one single model. So the report for this generalization analysis is an ePrint, if you want to have a look at. Okay, so yeah, so this finishes the part related to the research that we have finished, and I would like to share with you what we are doing. Sorry, yeah.
How do you combine you just combine the results of different neural networks, just averaging?
Yeah, so you combine you average, you sum and average the probabilities of the output. So that's it's very simple. Yeah, sorry.
Do you use overlapping test sets or are they separated?
You mean the training sets, or?
Yeah, the different.
So every network is trained with a different training set. So you have the no. So they are all so there is a 200,000 traces, and every time I randomly select 25,000 or 50,000. So it's like a cross validation in the end. Any other question? Okay, so so we are this year in 2019. We also want to analyze some other topics, and I think this is pending for a long time. But we would like to put some effort on that. That is to because now we understand more how to analyze generalization, how to understand how a network learns from traces. We want to make more progress on the assessment of hardware implementations when you have a lot of noise and parallelism and protections, to see if, because the deep learning community says that for deep learning you cannot make good progress if you don't use a lot of data. And then when we talk about a lot of data inside channel, we are talking about millions of traces. So we want to start analyzing a huge amount of traces to see how deep learning really applies to hardware architectures that are more, let's say, real world targets. And a second topic that we are, is still not defined if it will be applied this year, but it's an idea to reduce effort, time, and in leakage assessment. So the idea is to, just to summarize, when you do a leakage assessment for electromagnetic analysis, you need to scan your chip until you find the location of the crypto, and usually use TVLA or t-test for this as a reference. So the idea here is to use is to replace the search space by deep learning, where we make the deep learning to learn how many executions every spot is performing. So, and then the places in the chip where the network identifies better, with better accuracy, where it can identify better the patterns of the crypto in those positions, then we select to do a separate TVLA on that. So the idea here is to reduce this search space, to reduce the analyst time during the leakage assessment. So this idea is still let's say, growing, but it will be, I believe next month we're going to have more details, but the principle is it's very simple, but I think so if we meet the expectations, I think it will increase quite a lot the capabilities in the sidechain analysis. Yeah, so that was my presentation. If you have questions, I will be happy to discuss with you. Thank you very much.